Hello everyone, my name is Linus Calperdon, and today I'll be teaching you all about the basics of file handling in C. Here's our scope for today's short tutorial session. First of all, it's important to have a firm rationale when dealing with files and file handling in C. In the first place, what exactly are files? Well, files are a group of elements that are a collection of data stored in our secondary memory, such as our hard drives, for reusability and future use. Now, there are many different file types, but in the context of file handling in C and CCPROG2, there are two primary file types that we should be familiar with: text files and binary files. Now, these files are classified based on the way they store the data. I'll get more into that later. This raises the question, why exactly do we need files in the first place? Well, files preserve our data after our program is terminated. When working with software and programs in our computers, oftentimes the data that is being utilized is stored in our primary memory or our RAM. Now, whenever we turn off our computers or when we close a program, the data that is being used, that is found inside our RAM, is cleared and wiped. That's why it's important to have files that are stored in our secondary memory in order to have data that is readily accessible for use once again. At the same time, files saves us time for input and output processing through convenient storage and access. Rather than having repetitive scanf inputs and prompting the user again and again for data that we'll be using in our program, we can save time for that by having it readily available in our secondary memory and by reading to it from our program using a set of functions. So with that in mind, files makes use for efficient storage and access. Now, moving forward, the primary files that we'll be working with is text files and binary files. Starting first with text files, as you can see, are a few examples of text files that I've opened in a text editor, such as Vim and Notepad. Text files stores data in the form of ASCII characters. They are usually stored with the .txt extension, and they can frequently be opened with text editors of your choice. Now, as they are stored in characters, as data is stored in characters, we can often find the \n or the new line character found at the end of a line in order to indicate a new line. At the same time, how do we know that we've reached the last character in the end of file? Well, text files have a marker macro called EOF or end of file that indicates that, hey, we've reached the end of the file. This is all that you have. Now, when working with text files, since we're working with ASCII characters, it's important to recall that when we type in numbers in text files, we're representing them with their ASCII equivalents, with their character equivalents. We're not representing them as an integer, nor are we trying to say that, hey, when we've inputted 1, 2, 3 inside a file, we're not putting the integer equivalent of 1, 2, 3. Rather, we're putting the character equivalents of 1, 2, and 3 found in our text file. Moving forward to binary files store data in the form of course, ones and zeros. And the way it's being stored in our binary files is similar to the system, or rather to the behavior of how data is stored in our main memory, albeit this time it's stored in a binary file. Now, binary files are usually found with the .bin extension, but binary files can also have different kinds of extensions, such as .exe, .dat, and many more different extensions. And binary files can only be created from within a program, and at the same time can only be read by a program. That's why it's important to know beforehand what exactly are the contents of a binary file, because they are not easily readable to our human eyes. That's why it's crucial to be familiar with what can be found, or rather be interacted with, inside a binary file. So in essence, file handling and files in C provides us the opportunity for reusability of data, for portability of our data, because if we wanted to, say, store something in our computers and we wanted to use it on a different system, we can simply store it in a file, send it over our network or in a flash drive, and reuse it once again on a different system through files. At the same time, files gives us efficient input processing and output processing by having our data readily available through our secondary memory. And at the same time, it gives us the opportunity for storage for long-term use because it's stored inside a file that is found in our secondary memory rather than being immediately cleared out in our primary memory. So with all that said and done, we can now move forward to our basic text file handling in C. When working with text files in C or with files in general in the C programming language, we'll be working with file pointers. Now, the general syntax for having a file pointer, a new type definition, we'll be having the keyword file in all caps, and then we'll have, of course, a star to indicate its pointer, and a pointer name of our choice. A couple examples of its application is here. We have it here, we have the word file in all caps, a star or an asterisk, and of course, our file pointer name, where FP implies that it's a file pointer. Now, let's say if you want to have a file pointer that indicates it's an input file and an output file, we can also use this syntax as we have here. Now, recall, the file pointer is a type definition that allows us to store file information with the use of pointers. Now, when opening files in the C programming language, the first thing to do is to make use of the fopen function. Now, the general syntax for fopen is, of course, the function name fopen, followed by our file name, which is a string, and a mode, which is another string that is passed on to our keyword, or rather our function name fopen as parameters. Now, in the context of this function, our parameter file name is a string of our file name and its corresponding extension. So let's say if we have a file name called input.txt, we'd be enclosing that in quotation marks and inputting it in this parameter place. And now mode is the method of how we want the file to be opened. I'll be getting more into the modes later. Here's the function prototype for fopen. As you can see, it's roughly equivalent to our syntax for how and when we want to use fopen. Now, what exactly does fopen do? Well, after inputting the necessary parameters, fopen returns a pointer to a file if it does exist, but if the file isn't found within the current working directory, then null is returned. Fopen is helpful if you want to check if a file exists, and of course, with its baseline objective, when working with files, we'll obviously have to make use of fopen. To simplify it, similar to how we open files by double-clicking them on our graphical user interface or on our computers, its C equivalent of double-clicking would probably be something like using fopen. Now let's get forward to the modes when working with fopen. Now there are many modes when working with the function fopen, but primarily we can work with these four primary modes. Now, we have read mode if you simply want to read a file and work with its contents. We have write mode if you want to write to a file. Now, when working with write mode, we have to be careful because let's say that you have a readily made file and it has some readily made data found inside it. If we were to write to it, it will obviously overwrite the content and it will change it. That's why in the case that you simply want to add on to the data that is already found inside your file, you can simply use append mode, which adds new entries to the end of the file by starting at its endpoint. So here are some sample applications of using fopen. Now, in our previous slide, we've already declared our file pointers, and now we're returning, as previously mentioned, a pointer to a file using fopen. So here we can see fopen in action. We have our fopen function name, and of course our parameters. Our parameters of our file name. Let's say we have a file called input.txt, and we want to read it in read mode. Since we're simply reading input and be using it in our program, so we're going to be using read mode. Now, if you want to write to a file, to output.txt, we're going to be using write mode because we want to write our output to this text file. Now, let's say we simply want to append to a readily existing file. Let's call it file append.txt. If you want to add below it and add more data, in addition to the readily available data that is found inside that file, we can simply use append mode. And now when working with binary files, we simply append the plus b, or rather b in itself, to the previous modes that we have in mind. I'll be getting more into binary files later on. Now, when working with files, always remember to close your files after opening them with fclose. Keep in mind we're working with them through a program, which is our text editor. And if we forget to close our files after opening them, there is the implication or the possibility of data loss. As we recall, data is primarily saved in primary memory. So when working with files, after opening them, always remind yourself at the end of your code, or at least when you don't need to work with it anymore, always close your files. Now, the syntax for fclose is, of course, the function keyword or the function name fclose. And then inside, we'll simply just be putting our file pointer name. So in application, here's its keyword fclose. And then our previously defined function pointers, or rather, our file pointers, fp input and fp output. And then by simply putting them inside the parameters, we're effectively closing the files. And therefore, we can rest assured that we won't be having any data loss anytime longer. In putting those into demonstration, I've created a short program that simply checks if a file is present in our current working directory. So as previously mentioned, it's always important to work with file pointers in order to point to a file. And then we assign fopen to get the address, the file address of the file that we want to work with. In this case, we want to work with a file that is test.txt, and we want to read to it. Now, moving forward, we want to check if the file exists. Recall that fopen returns null if a file doesn't exist, and it returns a file pointer address if it does exist. And then we store that in the pointer of fp. And if this condition checks if it does exist, and if it doesn't exist, if it's equal to null, then we stop our program and output to our console that it does not exist. In the case that it does exist, then it ignores this, and it moves forward with the rest of our code. And of course, always don't forget to close our file. Now, after compiling and running it, we can see that in my current working directory of documents, and if we run our code, our file does not exist. That's because it's not present in our current working directory. But after creating a file with the command touch, and after running our code again, we can see that test.txt is indeed found. And that's how you work with file pointers, with fopen and fclose. Now, here's a couple of tips when working with these functions. You can always open and close a file multiple times in a program. So depending on your objective, you can open and close a file as many times as you want. And at the same time, you can also work with different modes in a file. So let's say after opening it in write mode, this time you want to read the newly written data to your file. And so after closing it, you can now open it again with a different mode. So keep those in mind. Now, let's say you want to print an output to your file because we want to use it all over again, or we want to store data for reusability and possibly future use. In order to do that, we can print our content or our data to a file instead of our console with stdout, but I'll get more into stdout later, using fprintf. The general syntax for the function fprintf is the use of a file pointer, a string format, similar to how we use printf. This is where we'll be formatting our string or our outputs in this case. And of course, the expression of the outputs that we will be formatting. In essence, fprintf is basically a generalized form of printf. Anything that we can do with printf, we can also be done by fprintf. Now, here's it in action. Of course, it's always important that our file is in write mode before writing to a file because we want to print our output inside the file. So here it is. Make sure it's in write mode with the string w. And In the case that we want to display our output to our console, it's important to use std out. Now, std out is not a file pointer, rather it's a readily available keyword that is found in our standard library with std out. And by simply putting std out in our file pointer parameter, then we can print our data or our variable values onto our terminal. In contrary, we can also do the same, but in the context of our files by using the file pointers instead. So here I have some code. Let's assume that we have variables that are user inputted, that we are prompting from the user. And then after prompting the user, we want to display these values or print them to our file. So here it is. We have our file pointer where we want to point it to or print it to. We have our string formats. So since we want to format a string and print a string, we're going to use %f. Since we want to print an integer, we're going to be using %e. And since we want to print a float with 2 decimal places, we're going to be using %.2f. And similarly, if you want to do it on our console, we simply use stdout as a contrary to our file pointers. After compiling our code, after running it, after it's been found, we'll be prompting our user for some input. And as we can see, we've successfully outputted it to our console using our fprintf and stdout. Now, let's say we want to see what's inside our test file. And from an empty text file that we've recently created, we can see that the output is indeed present in our text file from our user input. Now, let's say we want to work with inputs naman that are present from our files. So its counterpart of fprintf for inputs is of course fscanf. Now, the syntax for this is a cross between fprintf syntax and scanf syntax, where we have the function name fscanf, the file pointer of where we want to read formatted input from, the string format, and of course, the address of the file of the data type that we're working with, or rather of the variable that we're working with. Now, the counterpart for input, because similar to fprintf, anything that can be done by fprintf can also be done by printf and vice versa. We can also do the same with fscanf and scanf by simply using standard input as a placeholder for our file pointer. Here we can see it in action. So we will be declaring a file pointer, then we'll be declaring a variable called int, and then our address, our variable address of where we want to store our input data, similar to scanf. And then after prompting our user for input from the console, since standard input, we'll be outputting that to our console. So here we can see it running. You can see it being output. And now, let's say we want to work with it with a file. We have a readily available file with the contents of 36912. And we want to read this. So we'll be using, of course, a file pointer, fopen, and we want to read the data from the file. So we're going to be using fscanf, which read this line inside our input file. And then we want to output that to our console. So after tracing all of that, declaring first our necessary pointers and variables to be stored to, printing it to our console, scanning for user input, and then printing that user input, opening a file, reading data from that file using fscanf, and storing it in int and int's address, and then printing that out. By running our code after compiling it, we can see its corresponding output here. So that's what we want to do if you want to read input from a file. Now, some quick tips to read all present data found inside a file. Depending on what you're working with, you may have to create an algorithm that opens, reads, and scans files on each line of content until it reaches the end of the file. You can do this, of course, with the macros and the repetitive use of reading and writing and using lots of fscans if you want to do that. So as I previously mentioned, we can use with loops and we can use the aforementioned functions, thus making it possible to read multiple streams of numbers, characters, and different data found inside our files. Now, let's move on to more different methods of inputs and outputs. So to add data to a file, we can open the file in append mode. It prevents overwriting in contrast to using write mode and appends information to the end of the file. So here we have some code that I've written, and instead of opening it in write mode, we're opening it in append mode. I've created the for loop that will repeatedly prompt the user for some integer input using fscanf that is being printed or rather prompted through the console, and then we'll be printing this output to our file. So here it is in action. And if we open our file through our text editor, recall our previous file, we had these previously inputted. And as you can see, our user input of 369, 246, and 482 is now added to our text file. Rather than overwriting these previous information, it's added to the bottom. So that's how you'll be working with the append mode. Moving forward to basic binary file handling in C is similar to how you work with files in text mode, or rather with text files, but in the context of binary, you'll be using an additional set of functions. So basic binary file handling in C. When dealing with binary files, it's always important to know what you're working with ahead of time, since we won't be able to intuitively read and decode the data. And when working with binary files, it's important to append a -b or b to the mode to indicate that you are in fact working with the binary file. So as I previously mentioned, we also have a new set of functions to be able to read and write to binary files. Here is it in actions. If you want to read a binary file in read mode, we have our read mode of R, and we append a B to its end to indicate that we're working with a binary file. Now, when writing to binary files, in contrast to fprintf, we'll be using fwrite. The general syntax for fwrite is with the use of a buffer pointer, a size, a count, and file pointer parameters relative to its function prototype, which accepts a pointer, a size, the size of elements, and of course, the file pointer that we're working with. So when working with fwrite, it gives us the number of items written. In other words, it writes the number of bytes written when size is defined as 1. In the case of errors, it returns a number that is less than or equal to 0 than count. Now, I understand that the parameters at first glance or at the first time you hear it may sound very confusing. But think of it like this. Think of buffer pointer as a pointer to the block in memory to be written to the base address. So this is where in memory, recall that when working with binary files, it's similar to working with data that is stored in your primary memory, but in this case, we're working with the file. Think of it as a pointer to the block in memory that we want to write to, which is an address that we want to write to. Now, think of size as the size of each element, a collection of data that we'll be writing to. So let's say you have an integer, which of course has the size of 4 bytes. So we'll be putting the size of 4 integers. That's the elements that we'll be working with here. So that we'll be putting there 4. And think of counts as the number of elements that we want to write to on every fwrite. And then think of file pointer as the file pointer in itself that will output our writing content to our file. So this is its destination. So buffer pointer as the block in memory that we'll be writing to. Size as the size of each element that we'll be working with in bytes. Count as a number of elements that we'll be working with, or the number of elements that we'll be writing. And file pointer as the destination of all of these into our binary file. So here it is in action. So if we trace this, we can clearly see that we're opening a binary file in write mode. And then we're predefining, or rather pre-initializing and declaring a set of variables that we'll be working with. Now, since we're working with pointers, we have the option to create pointers to store addresses or to point to addresses. And then we'll be using those as a signifier that these are buffer pointers that we'll be working with. And recall that the size of determines the size of a data type that we're working with. So by using the size of operator, we're able to tell how many bytes are present in each of these data types, the data type of char, integer, and float. And since these pointers has this information stored, we're able to effectively write this to a binary file. And after closing that file, we're outputted with this data. So this is how it can be read in its natural or raw form. Now, a quick tip with regards to working with binary files. A similar process is used to store arrays and structures in binary files. Simply replace the buffer with the array with this array and structures address, and of course the number of elements to be written that is present inside your array and your structures. So let's assume that everything is already declared and predefined for the values of an array and of course our structure. And instead of having the buffer pointer, we can simply have those in excess because in essence, those are already addresses. And so we can simply input that in our fwrite. Now, let's say that we want to read data from binary files. To read data from binary files, we'll be using the function of fread. In itself, rather self-explanatory, the function reads data from a binary file and stores it inside a variable. So the general syntax for fread is the function name fread, followed by the parameters of address, size, count, and file pointer. It's rather similar to the syntax of fwrite. But in this case, we're simply reading from a binary file rather than writing to a binary file. So in this case, address, the address parameter, is the address of the variable that we want to store the data into. So in the previous one, fwrite, this is the address of the data that we want to write to or that we want to write with. But this time, this is the data that we want to read from or to store data into. So in order to do that, we can trace this program. Again, we'll be first opening it in write mode to create readily available data. And then after doing that, we'll be closing it. And then this time, we want to store this new data into these new variables in order for them to be able to store the readily written data. So doing that, we'll have to open it in read mode because we want to read from our binary file. And then we'll be using fread, pointing to the address of these characters. And then, of course, still using the size operator to determine what exactly we're working with and the number of elements. And from where exactly are we reading it to? So in this case, we're reading it from file pointer, which is our binary file. And then when we print those new variables, we can clearly see it being inputted to our console. So from this, in its binary format, to being read in our program, to being outputted to our console using printf, or if you want, you can also use fprintf here, but with the std out instead of a file pointer in it. Now, in working with binary files in C, there are a handful and an entire library of other useful functions in working with binary files, such as ftel. So when working with files, you can think of how our computer reads it from top to down as a caret. So when you're typing, you have a line that indicates where exactly you're writing to or where exactly you're positioned and reading to. Similar to that, we can use ftel. Think of it as the caret in the file that marks the current place that you'll be writing to. And we obviously begin at 0 at the very, very, very top of the file for every reader write. So for every reader write, for every addition or read to a file, our position will advance a number of bytes until we reach the end. And then the general syntax for that is ftel and then the file pointer that we'll be working with. Here it is in action. So as you can see, I've declared a file pointer in a binary file. And with its data type and file pos, I want to know where exactly inside the file are we currently reading at or working with. So it always starts at file position 0. And then after that, I declared some variables and initialized some variables with some values inside them. And this time, I want to display the file position after every write that I have to the file that I'm working with. So after writing to binary, I want to know where I'm working at. So I use ftell. As you can see, I'm now at position 4 because 4 bytes are stored because it's an integer. And then another write, we can see that we're working with another place in our binary file. And then now, moving forward, working with the float, we move 4 bytes again in memory. And then finally, at the end of our file, we can see our current position or our final position, which is 12 bytes. That's how much data is stored inside our binary file. And that's how you work with ftell in order to tell where you are inside your file. Now, let's say you want to read and write simultaneously without opening and closing your file multiple times in your program. With that, you can use these modes, RB plus or R plus B. But the difference between these two modes is how it's a requisite to understand that to use this, a file must readily be existed. But when you use this, it creates a new file, or rather, it creates or overwrites a readily existing file if it already exists. So keep those in mind. Again, when working with files, you have a macro, EOF, that indicates the end of file. And if you want to check if you've already reached the end of the file, you can use FE of F to check if you've already reached the end of the file. And if you have reached the end of the file, it will return a non-zero value. It's also useful for looping in the case that you want with an entire set of documents or an entire file content, and you want to do something repetitively until you reach the end of the file. FE of F would be helpful. Now, if you want to manually set your position in the file, you can use fseek. It sets the file position indicator or the caret, quote unquote, to a new place to read or write relative to the origin point. So if you want to move somewhere into file, you got to indicate where you're starting from. If you want to start from the end of the file, from the beginning, from zero, or if you want to start right after a new byte is written. And you can do that with fseek and this syntax. Of course, we'll be working with a file pointer. You'll be working with an offset. So where exactly do you want your caret to be positioned relative to an origin point? Do you want that 4 from the top, 4 from the bottom? Something like that. And in order to indicate your origin point, you can use these origin macros such as seekset, seekcur, and seekend. Seekset is used if you want to start relative from the first byte. Seekcur if you want to start from the current position that you are, and seekend if you want to start from the end of file. Note that the position indicator is always the origin plus the offset. And that's how you'll be able to work with your files and declare and tell your program where you want to be inside a file by moving its position with fseek. Here it is in action. Let's assume that we have an empty file and it has some readily available data inside it. So obviously, we always start with 0, and then we'll move forward with fseek. So we want to move 4 bytes forward. We'll be using f position, and then we'll be moving 4 bytes, and that's our current position now. We want to move 4 bytes to our current byte, relative to our current byte. And then right now, our current position is at 8. Now let's assume that the size of our file is now at 8, and we want to move from the bottom going back. So we use a negative value from the end, and we're back at the 4th byte position. And with this, using fseek, you can now access elements as you please. And with that, that ends our basic file handling in C. If you want to know more about how to deal with files in C, there's always a handful of resources that you can work with. You can have the book, the C Programming Language Book by Brian Kernighan and Dennis Ritchie, creators of C, the CS50 manual pages that contains an extensive documentation and explanations for the C standard library and others. And of course, you have your other resources such as Geeks for Geeks, Tutorials Point, and Programmist for additional resources on working with file handling in C. So that concludes my tutorial session for working with files in C. Thank you very much, and I wish you the best for your CCPROG2. Take care.